Well, hello, welcome back. Um, Today we are going to discuss, um, go through a basic introduction of stochastic calculus, and then we look at Ito's integral, um, and properties of Ito's integral, and maybe some well-known facts, how to use chain rule, Ito's Dublin formula, geometric bounding motion, asset price, distribution of rate of return, and maybe like we'll cover the basic model as well. I think I might skip over this, but let's start. Um, so, well, let's start with Ito's integral. I've got my favorite highlighter here. The goal of section is to define so-called Ito's integral, which is stochastic integral of the form sigma u dwu, where sigma u is a stochastic process and wu or wt is a standard bounding motion. And in addition, we observe as time passes the realization of bounding motion gives us information. We assume that the information available at time t is sufficient to know that sigma with certainty up to time t for each t in 0 to t. We define only the stochastic integral for integrand satisfying this condition. That means that standard bounding motion is the only source of uncertainty, and that is that there is no additional source of uncertainty that is introduced through sigma u. So bound motion is the only source of uncertainty here, and then there's no uncertainty, which obviously in context of financial models of finance or in real life application is, I think it's false. I'm not sure if I think it's false. I don't know how to prove that, but it is. Maybe we'll look at the proof of that. We describe the procedure of defining the stochastic integral. First we define the integral of piecewise constant integrand sigma, and then pass on the limit to extend it to general integrands for a partition of 0 to t. 0 equals to t0, and t0 is greater than t1, and t1 is greater than t2 is greater than t1 is greater than t0, and t2 is greater than t1, and so on, and tn is equal to t. And we assume that the integrand sigma is constant for each subinterval tj to tj plus 1. Sigma t is equal to sigma tj for all t belongs to tj to tj plus 1. So basically it says that between an integral sigma is constant, and it's a function, so basically it's a function of t, but between two intervals or between decimals, I think it's constant. So I think like that's what this means. Now we define process it, which is equal to sigma t0 wt minus wt naught, which basically means that it's an Ito integral for between time durations t and t naught, and using the formula, the property of the bounding motion, this is equal to sigma naught wt. So this is equal to wt, and this is equal to 0. So this is sigma naught wt. Now again, it can be divided into sigma naught wt1 plus sigma t1 wt minus wt1. Basically, I think I've explained it in the previous videos. Basically, this means that something like this exists, and let's say this is 0, this is t1, and this is t. So this plus this So this is w t1, this is w t minus w t1. So this is basically how you write wt. So it's just another way to write that, nothing else. Okay, well, yeah. And after doing this, wait, now they did the same thing with T2, and then they made these two variables, or these two uh, components of things. And then finally the equation can be broken down into smallest components and differences of those components. A financial application of Ito's integral. Sorry guys, I'm a bit sleepy. WT represents the price per share of an asset at time t, warning that downward motion may take negative value, so it's not really appropriate for modeling the price of a stock. The partition 0, again with the same property that t naught is 0 and t n plus 1 is greater than t n forever, represents the trading dates and times. Sigma naught t, sigma t naught, sigma t1, sigma t dot sigma tn are the positions in the asset, number of shares at each trading date, and held until the next trading date. It is the accumulated gain slash loss leading up to time t. Let sigma t be a process satisfying the condition stated earlier and satisfying the technical square integrity condition. E integration 0 to t sigma u square dt is less than infinity. Basically it's evolution of position held. Right, I think so. We define a sequence sigma n t of piecewise constant processes which converges at sigma t as n tends to infinity, I as n tends to infinity, e of sigma 0 integration of 0 to t, integration from 0 to t of sigma n t minus sigma t mod whole square dt equals 0. We define the Ito integral by setting an integration function of the Ito's integral, which basically gives us the integration of Ito integral with limits, where the limits are mean square sense. I don't think that has any applications. Maybe that gives us some properties. Let's look at some properties of it. Properties of Ito's integral, we simply list below any proof, some useful properties of, without any proof, some useful properties of Ito integral. It is continuous in time t. So Ito integral it is continuous in time t. The information available at time t is sufficient to know I with certainty up to time t. So if the information available at time t, so that information is available, we can determine value of I until time t. So this value can be determined if we know other information. Maybe this, okay. Yeah, Ito's integral is linear, which means that basically C1 sigma 1 u plus C2 sigma 2 u dw u, integration of this value can be written as this value, which is basically uh, that you can write it as two different parts. Uh, IT is a martingale. So this is an important property. So Ito's integral IT is a martingale. Ito's isometry. So I square t is equal to expectation of I square t is equal to expectation sigma u du is integration. So E of I square t equals E of sigma u du. The quadratic variation of Ito's integral is I t sigma t sigma u du. Just give me a second, guys. Now let's look at some additional results of the Ito's integral. The first, there's a theorem related to it. So given this Ito's integral, sigma s is a deterministic function, then IT is normally distributed with mean 0 and variance. Sigma square s ds is integration with finite limits of 0 and t. So IT is a Gaussian process. Normally distributed with mean 0 and variance sigma 0 to t sigma square s ds. Now let's look at some of the most important properties of stochastic calculus. These three laws are very crucial. So if we have double integration, or if we have this thing here, it can be written as dwt can be written as dt. Since the quadratic variation of the differentiable function is 0, we also have dt equals 0, and lastly we have dt equals 0. Actually, this is something you can actually deduce from the nature of the process as well. So like you can so dt and dt are sort of constants in time, so basically their differentiation or the change between them, I think that's what it represents. Okay, their differential form. So since like they are sort of constants, their differential form is 0. And these are like two processes, and these processes both depend on time, so I think that's why it is equal to dt. And since like this is constant, this something like that. I think you differentiate them with chain rule. I'm not sure how we come across this. I forgot how to derive this, so Let's move ahead. But remember, like these are the three most important formulas that we need to remember going ahead. At least they're used a lot in quantitative finance. I think they are also used in derivation of Black-Scholes formula. Let's move on to the chain rule of stochastic calculus. So any function with respect to a Brownian motion or a function that uses Brownian motion needs to go through this chain rule of differentiation. Oh wait, this is the chain rule that we have in the ordinary calculus. But for this stochastic calculus, the chain rule is given as dfwt equals f dash wt on dwt plus half f double dash wt dt. Okay, so this is also a very important formula that you need to remember. I've written it down in my note. The formula is also called E to Dublin formula. It is interpreted as the differential form of E to Dublin formula in integral form. FWT is given as f naught plus integration of f naught f dash fs fws dws plus integration of 0 to t half f double dash ws ds, where 0 to t f dash ws dws is an stochastic integral, which is usually of the form that we just saw. Basically it's an integral. It can be generalized to functions who also depend on time variable, so you can write them as so if you have a mixed function with a multivariable equation, you can rewrite the E to Dublin formula as ft. Basically you have to take partial differentiation of the variable with respect to both of the processes, both of the variable that it is related to, it is dependent on. Okay, yeah. I think so. Remember, this is also very important. So process X is given as basically this. So I think that's it for this video. In the next one we'll discuss geometric Brownian motion and price, distribution of rate of return, application of quadratic variation in Brownian motion, and maybe we'll discuss this. Yeah, till then, enjoy, have a great day.